Hello? Yeah, perfect. Okay, so thanks for coming back. As most people in our room know, but not necessarily people on the live, there was a fire alarm, so I'm going to have to shorten the presentation to try to stick to schedule. So what I want to do is a quick update. I mean, it was supposed to be longer, but yeah, a quick update about Ethereum 1.x. So very short summary, Ethereum 1.x is the effort that is trying to keep Ethereum 1 alive until Ethereum 2.0 comes, it gets delivered. And we focus on the EWASM aspect of it. And the scope is fairly easy, fairly simple. We just need to support WASM precompiles. So precompiles are contracts that are not written in like the EVM bytecode. They're supposed to be called very often, and these are repetitive contracts that get called over and over again. So they're usually written in regular like the language that your client is made of, is using. Why do we want to do EWASM precompiles? Well, it all comes with the fact, like Ethereum 1.x, the focus is on reducing the size of the state. So if you need a new primitive, you want to be able to you want to be able to not duplicate it. You want to be able to create this contract and make sure that everybody calls the same contract instead of duplicating the code for a new curve over and over again. And so WASM is pretty interesting for that because you have a lot of languages available. It's fairly deterministic, so it's a good starting point. And yeah, you can just add features. And if you like you have interpreters available, so you can add the interpreter to your client. And if you have a new contract that you want to declare as a precompile, you just distribute it to every client. Every client uses their VM, and it can be supported pretty quickly. So the current state is that all existing precompiles, like those who are currently existing, have a WASM version. There's a version of Guess running WASM precompiles. It's using Wagon. And it passes the test suite, and there's a full Rinkeby sync, and there's a mainnet sync. It unfortunately goes until block 2 million. After that, the machine I ran the test on ran out of memory, so I could not get the full data in time for this presentation. But the problem was my machine and not the precompiles themselves. So I don't have much time, so I'm going to skim over this. But basically, the information you need to get is that the purple here is the WASM. The yellow is the original, like the comparison. This is a Rinkeby sync, and you can't see that, but the scale is logarithmic, and so that means like it's actually much faster, much slower. You can see this is the ratio, like the average time it took to execute the WASM contract versus the average time it took to execute the native version. And there's some actually interesting facts. For example, this is the identity contract, so it's just a data copy. And it's actually quite surprisingly, like there's quite a slowdown. So that's the good news. That means like at least you understand that copying data is actually something that takes time, and so as a result, that gives way to that gives an interesting series of leads for optimization. The other good news is that those two contracts are actually not used that much. So that's an interesting case as well, and that kind of brings like fodder for the point I was going to make further down this presentation. The other thing is this one. It's the modular exponentiation. I wrote it in a hurry, so it's actually not optimized at all. So I also have a good hope to optimize it in the future, shortly actually. If you compare Ringcubi and like the Ringcubi test and the mainnet test, you can see this is one. So it's actually pretty similar. I mean, there's a big variance, but I expect the times to be roughly the same. Right. So just skimming over, but basically the idea is that obviously we're not going to replace the existing precompiles based on those numbers. What we want to do instead is just use WASM to introduce new precompiles, like new features. You can just have it ready. All you need is to have a WASM interpreter. You put your contract, like you distribute your contract. Every client can immediately enjoy benefit from using your contract. And then over time, if your contract gets really used often, this is when it will start getting optimized, translated into your native language. But it's really meant to make adoption of new precompiles faster. And the next step, at least the one I'm taking, is to think about to study ahead of time compilation. And ahead of time compilation, you just have your WASM binary. You turn it into something that your machine understands. So most likely, I wrote x86. It's most likely AMD 64, but I just wanted to write that here because WASM is 32-bit and so is x86. But yeah, so the idea is you've got your binary, you compile it into native code, and then you load it. This represents your process addressing space. You've got geth at the top, very integrated, very self-reliant. You got the libc at the end, and you just load your x86 binary as if it was a library. And then what happens is that you just cross your fingers, you jump, and you regret it immediately. But the information is, most of the information is not really useful, because what really happened is that, once again, geth is very, very self-centered. So you don't get much information from this stack trace. However, the interesting information is right here. You can see the program counter is 0. And so that means something wrong happened. And then you investigate. So the reason why I'm sharing all this information is for people who would be interested in doing the same kind of work for their own client. I'm just sharing some experience. So what you do is you can see the translation, the software that translated the WASM into x86 or AMD 64 binary uses this kind of weird return trick. It takes RCX, the content of RCX, which is a register, puts it on the stack, and RCX was 0. So what turns out on the top of the stack is 0. So when you return, you just return into invalid memory. And the real value that was supposed to be in that register was this. This is part of the RET's, what's called the trampoline. So it's, there's a lot of confusion. That's what I wanted to say. Unfortunately, I don't really have time to detail that because of the alarms. So if you are interested in the details, please come talk to me. So the issues, like the more high-level issues that I ran into, it's memory allocation. Memory.grow doesn't really work well with the library that I use, the software that I use. It's called WAG. It's fairly new, so it's perfectly understandable. The problem is also with the Go runtime, because once again, geth is very, very integrated. So they use like stack pointer. Everything is in this area, and then when you jump, you basically play with the devil. Like the good thing about Go is that it gives you a binary that relies on very few external libraries, like just the libc normally, and you can just distribute it all over the place. Here, you just break this contract, so you have to deal with the consequences. So you can't really, before calling, like when you call a compile contract, you will have to, if you want to call back into the Go runtime, you have to make sure that you translate between the two worlds. And then, yes, all the EEI and how to simply terminate the contract, that hasn't been thought through yet in the compiler, because most compiler, at least the one I use, is just meant to compile it once and for all, and then at the end of the program it just exits, which is not what we want to do when we write contract. We want to be able to reuse that code over and over again. So yeah, these are the two things that need some attention. The way I got my my information, I'm really going to skim over that, but it's basically to use GDB to patch the stack and everything as it goes. So I just fix the stack pointer. I say, okay, you're off by this much, and I just switch to C to be able to like modify the content of the RCX register, and then I go back and I continue. So it's a lot of breakpoints and scripts to fix that, to be able to basically analyze the contract. And then of course at the end you need to sanitize everything and make sure you go back to go. So the next step for 1.x, there's a lot of work happening with the benchmarks. Hopefully there's going to be some info about this tomorrow. The big question is metering. How do you want to do the metering? That's actually a fairly important question. The precompiles, they just have a formula. They just take the input data as a base. They calculate how much gas it's going to be, and this is what this is how you account for the gas. Whereas regular contracts, you call use gas at some specific points, and that's not something you really want to do. So the exact methodology is still being discussed, but like I would say the most likely is that we're going to do that on a case by case. Case by case. This is at least my opinion. Some other team members might disagree. And then we need to select the series of precompiles that will make it to the release. So I think we've got one for ZK snarks, but if you want another precompile, come talk to us. And then there's the deployment proper. And so I went a bit fast because once again we need to catch up on the time. I guess, I don't know, if you want to, maybe I can take one or two questions.
Why, in the benchmarks, why was the WebAssembly so much slower than the native?
Right. So there's many reasons for that. First, the interpreter that I picked was like the slowest I have ever seen. It's something that is kind of experimental. There's also the data copy, a lot of data copy that's inefficient. There's let me think of the top of my head. There's there's the fact that it's interpreted, so it's going to be slower anyway. And what else could I? I think these are the main factors that I foresee.
One more.
Thank you for the presentation. And the question is about 1x and 2.0, how the WASM implementations for these two projects will work together. Is it exactly the same teams working on it, or we have separate approaches? There might be some discrepancies. Is it just some help for the future work on 2.0?
Right. So there's indeed, that was supposed to be part of my introduction, but unfortunately it was rushed. So thanks for asking that. The role of 1x is indeed to keep 1.0 alive, but it's also kind of prepare the ground for what comes next. And Wasm is the prime candidate for being the execution engine for 2.0. So that's a nice way, like the precompiles, it's a nice contained way to experiment with that in preparation for 2.0. So do we work together? Yes, absolutely. Are we the same people? Some people do 2.0 work. I mean, I'm more focused on the 1.0 work myself. I'm a member of the guest team. Yeah, I mean, we talk. It's definitely going to. We collaborate. We're having calls to make sure we're aligned. Sure. All right. Well, thank you for your time. And sorry that it was a bit rushed, but are we back on on schedule?